everyone. I am really ecstatic to welcome Daniel to London. It is his first time speaking here. We've actually wanted to have him speak with us for quite some time, but we needed to wait until we had a big enough room. So thank you all for coming.
Thank you. Hey everyone, this is Daniel for Rock the JVM. And you are watching How to Macro in Scala 3 and why. So I just released a long-form course on Scala macros and metaprogramming. If only I could make these displays swap. All right, so this is my, no, not the correct one. Right, you know what? This is the one. So I just released 3 weeks ago a big course, a long-form one on Scala macros and metaprogramming. This is something that teaches you how to manipulate type-safe Scala code with Scala at compile time in the same compilation pipeline, which is pretty goddamn magic. So you can learn pretty much everything you need to know about inlines and macros and the kind of compiler manipulation and AST programming that Scala can do. I made this course because aside from the Scala compiler team and a few poor souls who learned this on their own and made libraries and stuff, very few people know about this stuff, and I thought it would be great if more people know Scala macros and metaprogramming so that you can build awesome libraries, and that could benefit the entire ecosystem and community. So if you want, you can check that out. I wanted to add a gift for the Scala, the London Scala user group. So I added, on the Rock the JVM website, I added a little discount. You can use this code, London Scala, for 25% off everything I have. So you can check it out if you want. Unlimited, so everybody can use this code without any limits. Now, the goal of this little presentation is much less a presentation. As you can see, I have 2 poor slides, really. I wanted to do more live coding instead. So the objective of this little presentation is to understand what macros are and how they work, and a bit of what macros can do and why, so that you can build awesome libraries and some to demonstrate some realistic use case of the capabilities of macros. Obviously, this is pretty much a live representation of a little chunk of that course that I was talking about, the Scala macros and metaprogramming. So if you like what I'm talking about here in this presentation, you might want to check out that course. Now, I'm going to sit and write some code. Hopefully, now, honestly, I didn't expect this big of a room. So I'm a bit nervous. Forgive my mistakes in writing code. I'm going to try to fix them as much as I can. So I'm here in a beautiful blank SBT project. This is very, very vanilla Scala. The only thing that I've added is a compiler flag here with post and lining, so that we can see what kind of code the Scala compiler generated for us. And with macros, this is increasingly important. And I also added a unreasonably huge max inline, so that just in case we hit a Stack Overflow error, which I really hope I don't, we might want to see some of that output. And otherwise, this is just blank Scala, so we can very easily follow along. Now, can you raise your hand if you know what an AST is? All right, so a lot, but not everyone. Okay, so an AST is something that represents programs in the data structures of the compiler. So let me imagine a little programming language for something that's comparatively simple, like a math calculator. So when you type in a scientific calculator, like 2 plus 3 times 4 and sine 30, so 2 plus 3 times 4 divided by 5 and so on and so forth, and then you type compute or equals or something like that, that calculator has to take this expression in natural language or in the syntax that the calculator allows, and then evaluate it according to the rules of normal arithmetic. Now, it's not as easy as just taking all the tokens and then taking all the operations one by one, because there are rules to that. which is why I wanted to represent this very simple language in a data structure. And I would represent that as an interface. I'm going to call that expert. And this represents pretty much every token that you can put in this simple programming language. For example, I can have a case class, for example, a number with a value which is a double, and this extends expert. This is just the representation of this token. And then you have case classes for pretty much all the arithmetic operators, like adds with a left-hand side, which is an expert, and then right-hand side, which is an expert with a capital E, and this extends expert. And then you have all of these for subtract, for multiply, and then for divide. And then you can add other things as well. For example, you can have powers, or you can have a case class, maybe a sign, maybe you can say plus sine 30, something like that. Scientific calculators do this all the time. And then you can have sine with an expert as an expert, and this extends expert, too many experts. You get the idea. So the kinds of stuff that you can represent in this mini programming languages are essentially instances of this trait expert. So the way that the calculator would have to compute this expression is to parse it out into this sort of trait. So this particular expression, like 2 plus 3 times 4 divided by 5 plus sine 30, would be, for example, a sum, where the right-hand side is a num2, and then the right-hand side is this other thing, which is another sum. The left-hand side is this. So we have a multiplication or a division. These things are commutative in this case. So a division between the left-hand side is a multiplication between num3 and num4, and the right-hand side is num5. And then the right-hand side of the sum is sine with num30. You get the idea, right? Does this make sense? All right. This, my friends, is called an abstract syntax tree, or an AST for short. This is the data structure that is appropriate to represent this expression written in quote unquote natural language, or in natural programming language for this particular instance. Now, in the case of a much more complicated programming language like Scala, obviously we can have many different kinds of expressions, like class definitions, imports, expressions, method arguments, types, lambda functions, and so on and so forth. So every piece of Scala code that you can isolate, you can represent that as a node in this abstract syntax tree. All good so far? All right. Now, the idea is for a macro to be able to take this sort of abstract syntax tree and process that, manipulate that to obtain another abstract syntax tree, and also manipulate that with the same language, which is, I don't think you realize how powerful, magical, and difficult, impossibly difficult that thing is. For other programming languages like Lisp, this is comparatively easy because the language itself, the structure of the language or the structure of the code is the same as the structure of the data, which is a simple goddamn list. You just manipulate that list and you obtain another list, which you can then interpret, and then you can expand as the code runs. But in a typed language like Scala, this is impossibly difficult because you either lose access to the host language like Scala, or you have to resort to some other kind of magic, which other languages usually resort to text processors, where you simply inject other pieces of text that you can then compile with the rest of the code, or some other forms of backwards kind of manipulation where you lose access to the host language. In Scala, that's not the case. So Scala is pretty magical in the sense that the ability to manipulate this abstract syntax tree can be done using the same Scala language, with the same data structures, with the same standard library, with the same capabilities, with the entire Scala syntax, which is very powerful. And that is called a macro, or the ability to process abstract syntax trees is called a macro. Now, I'm going to show you what a macro is built of. And a macro has some special syntax in Scala, and it's built out in 2 steps. That's because in the realm of compilation, you have essentially text and then binary. All right. Now, before we have binary, we have a bunch of phases. So between the text, you have this AST, and then you have the binary by interpreting or turning that AST into something that the computer can evaluate. Now, this is a very simple compilation process. In Scala, we have several dozen compiler phases, not just like two, the way you see here on the screen. And for macros in particular, Scala also gives us the ability to separate the AST from the binary and allow us, kind of like an API, like here, to manipulate the ASTs with a macro and re-inject it back into the code into another AST. So this is kind of like a backdoor into the Scala language that allows us to manipulate ASTs in the compilation pipeline using the same host language, which is pretty magical. So this is the kind of area that we operate in. And macros are built into in two pieces. One is the ability to quote an expression into an AST. So the ability to turn this expression into this AST is called quoting. And the reinsertion of the AST back into the code into the same compilation pipeline is called splicing. So we have macros built in two phases. One is called quoting, and two, we have splicing. Okay, all good so far? All right. Now, in the Scala macros course, I spend like an hour talking just about that. But just in the interest of time, we're going to demonstrate the act of quoting and the act of splicing. Okay. Now, let me define my first macro. All macros are inline methods. So inline method, I'm going to call this first macro. Let's assume that this first macro takes some arguments like a number, which is an int, and a string, which is a string, and this returns maybe a string. Okay. Now, in order for us to process an AST into another AST, we have to quote some expressions. And usually the way that we quote expressions is to quote the parameters of the methods that we are calling. So for example, in this case, if I call first macro, I would like to quote the number and turn that into an expression, and quote the string and turn that into an expression and process those expressions into another expression. So I'm going to splice so this is the syntax for splicing. So splicing means this. So dollar with some curly braces, and here you have an AST, and then you obtain a value. Now, for quoting, it's the reverse. You take a single quote and some expression, and you turn that into an AST. Okay? Now, in order for us to return a final expression, you have to do both. We have to splice quote and quote, which is why the way that macros are usually implemented in libraries is to splice another method, which is usually a first macro, and usually it's suffixed with impl. And then you pass any sort of arguments that you like, usually the quoted versions of these parameters. I'm going to say number with a single quote, quote string with a single quote. That's it. Now, obviously, I have to define it. So I'm going to have a define for first macro impl, and then I'm going to have these expressions. So I'm going to have my number expr, which is now an expr of int. So you can see that the Scala language itself has a very similar representation to this toy calculator thing that I discussed. I'm just going to comment this out so that we don't have any naming collisions here. So we have an expr of int, which is essentially an AST, an expr a. So an expr a is an AST that when evaluated or when injected, it will turn the expression into a value. Now I'm writing these comments because I'm going to share this code on GitHub, by the way. So they might seem useless, but they might serve as a good reference in case you want to read the code after this presentation. All right, so we have this first macro impl where we have the number expr, which is an expr int, and string expr as an expr string. And finally, if I want to return a string at the end of the method, I'm going to return an expr of. So expr of. For now, I'm just going to build an expr myself. So I'm going to say expr with this is Spark. All right. This is our first macro. So here, what I have is a compilation error because the expert thing does not exist. I just started a compilation, a tilde compile in SBT. So in order for us to access this expert, we need to import, we need to add a little import. I'm gonna have import for scala.quoted.star, or you can simply say quoted.star because all the Scala packages are automatically imported. Now, in order for us to run a macro, we also need to pass an implicit value, which in Scala 3 we use a using clause. So using, and we have an API that is offered to us via a data structure called quotes. So I'm going to say using quotes. Now I'm going to add just the type. I'm not going to add this as a variable. I could. I'm going to add it later to demonstrate reflection, but you don't have to. So quotes gives us access to the ability to build expressions. And at this point, the code is a success. Now, this, what you're seeing here, this final module class macros demo usage is this the compilation of this very poor object over here, which has right replace whatever the Scala compiler generated for us. Okay. Now, if I have, for example, macro demo usage of val x equals 2, I'm going to see that in my compilation in my SBT. All right. So everything that I write in here, you're going to see in the compilation output. Now, what I wanted to demonstrate here in my first macro implementation is that if I call this first macro function with these arguments, for example, val first macro value as first macro with a number like 42, of course, and the string Scala, I'm going to save it. Look at this. We have first macro value defined as a string, and the compiler already knows that the string is the constant. This is Sparta, meaning that this first macro thing runs at compile time. This is super important. So everything that you write here happens at compile time. By the way, I'm using two different files here, one to define my macros and one to use the macros. That's just a restriction due to how macros are being compiled, right? So whenever you want to define macros, you have to define them in a file. And if you want to use them, you have to use them in a different file. That's usually not a problem because macros are usually defined in libraries and you use libraries from somewhere else. So that's usually not a big deal, okay? All good so far? All right, cool. So this is the first macro implementation. Macros are built in two phases. One is quoting and two is splicing. Okay. Now, macros are very powerful in the sense that you can build expressions yourself depending on some conditions. So for example, if I create an inline function, actually, let me, instead of having a constant expression, let me manipulate the code and generate different expressions depending on the values that we have in here. For example, if the expert int is a compile time known constant, I can surface that value out and I can do some checks on it. For example, I can say val the number as num expression dot, and there are many methods that you can use. There's one called value or abort. Value or abort surfaces out the value of type int in this expression if it's known at compile time. If it's not known at compile time, it will surface an error. So I'm going to say, for example, expert can say the number is, and then I can inject the number. And as I mentioned earlier, have access to all the Scala functionalities like S-interpolation, implicits, all the data structures, the standard library, and so on and so forth. If I save this, look at this, the number is 42. That's because I passed in the value 42 as a compile time known constant. If, for example, I had a method like give me meaning of life, which is obviously 42, I don't know who questions that. If I call the give me MOL, this is not a compile time known constant, which is why I'm going to turn an error. So macros are very powerful in the sense that sometimes, if you need, you can bring the value that is known at compile time into the realm of the macro and do something useful depending on what you want. For example, I can say val the string is, you get the idea. So I can say a string expert dot value or abort. And I can say if the number is less than 10, I'm going to say return an expert of whatever. I can use any sort of expressions here. The value is, I'm going to say, the string dot take the number. Else, I can say expr of many repeats, and you can inject any sort of expressions that you want, like the string dot repeat the number, something like that. Okay. Cool. So right now I should have, okay, expected meaning of value. All right. I have to save all of them. Okay, so many repeats. We have Scala repeated exactly 42 times. So all of the code that you write here, so this runs at compile time. So you need to be very careful what kind of computations you run inside a macro because, and now I think you can draw the dots now. You can connect the dots. There are libraries that cause very huge compilation times. It's one of the reasons why. Because if you want to create automatic serialization libraries or automatic type class derivation or many sci-fi features of Scala, that may increase compilation time, not least because of this, because the macro implementation runs compile time. All good so far? I want to show you some features of macros, and in particular, I wanted to show you that the API is very powerful in the ability to process ASTs and do quotes. For example, let me define my method. It's called this pattern matching on options. You're going to see why. This pattern match on options will take as a value, as a parameter, an option as an option int, let's say. And this returns a string. And I'm going to follow the same pattern. So I'm going to have splicing of a quoted code like PM options impl on the quote opt. This is a regular pattern. So you define a method inline def, you have some expressions, and then you quote them, and then you splice that back. So I'm going to have my def PM options impl with opt as an expr of option int. And this returns an expr string. And I want to do some pattern matching on options. Now, we know how to do pattern matching on options. We can pattern match on some, we can pattern match on none, extract the values and such. With expressions, Scala even has extra syntax for to give us the ability to figure out the expressions that this particular option was built with. For example, I can say opt match. So this is now an expression. So I'm not pattern matching the option itself, but the description of that option, the way that it actually occurred in the code. And I'm going to have a case. I'm going to show you a new syntax here. Quote, and then curly braces. So if this expression matches the following representation of the code, like sum42, then I'm going to say an expr with I found the meaning of life, obviously. In case I get a quote for some with some other kind of expression, like we have variables inside quoted pattern match, and normally we have some x, but in the realm of quotes, we need to splice them. So we prefix this with $, and this x is now an expr of whatever else. In this case, we have an int, and this is going to be known at compile time. So I'm going to say got a variable. So I'm going to have an expr with got a variable, and then I'm going to inject x. Or I can say x.show. There is a function to print or to display an expression. And in case I get something else, I'm going to say expr with got something else. All right, let's see if I have any compilation error. No given instance of quotes, yes, because I forgot the quotes. So I'm going to say using quotes. So notice that this using quotes gives us also the ability to print an expression. So now we have a string. Okay, and let me test this out. So I'm going to have let's say PM options demo. Type properly. I'm going to say PM options for sum42. Again, this happens at compile time. So we have PM options demo got something else. Why do I have PM options? Yes, because I will need to inline my options. this is something else that I wanted to show you. You know, by the way, I didn't ask about inline methods. Everybody familiar with inline methods? So inline methods essentially copy or replace all invocations with the body of the method at call site. That's what the inline method is. And the inline parameters will also replace all usages of the parameter with the expressions that they were used to pass as argument. Cool. So now that I've made this this option int inline, I can now tell the compiler to pass this expression literally here. So when I quote it, I pass the expression instead of PM options impl with the option 42 that I passed in here as argument, I'm passing the description of sum42 literally as a parameter to the implementation of the macro, if that makes any sense. So the pattern match now gives me, I found the meaning of life. That's because this sum42 was the literal thing that occurred in the code. If I have PM options demo version 2, if I have sum43, which is obviously a bad number, I'm going to have got a variable 43. If I have, I wanted to show you something. If I have v3 as PM options with option 42, at runtime, option 42 and sum42 are the same instance or are the same object or equal objects, but they're not the same piece of code that I'm passing as argument. So this sucker over here is going to give me found something else. Look at this. I got something else, even though at runtime, sum42 and option 42 are the same object, but they're not the same piece of code. So it's very important, and it's also very powerful for us to expect or to pattern match the exact piece of code that we're interested in. Is this cool or not? This pattern match can also pattern match even more complex expressions. So I was talking to Nicolas before the talk started, and I gave him an example of a chain of transformations on lists. So for example, if you want to do data engineering and you want to traverse a data structure and you map that data structure, like map function 1, map function 2, map function 3, that takes 3 passes over the data. You might want to optimize that and detect the chained maps and just compose the functions and run the composed function once instead of running multiple passes over the data. You can do that with macros. For example, I can say inline function, let's say list expression as taking a list as a list int. This list int is going to be inline. And this list int can be an expression of the sort list expr with list 1, 2, 3, assuming that this is like a huge data structure, like map function 1, like map function 1, map function 2, and so on and so forth. So let's say I have map function 1, map function 2. I can pattern match this exact expression with a pattern match, compose the functions, and then run the final transformation. Let me show you how that would work. So this is going to be a list int. Let's say that this is the optimized version. So let's call this optimize list. And I'm going to splice encoded code. So I'm going to say optimize list impl on the quote list. So I'm going to write that function like optimize list impl with my list as an expr list int. And this is going to be an expr list int. And I'm also going to pass my using quotes. So using quotes so that I don't miss out on any API. And I'm going to say, for example, list match. And in case I get a quote, and inside these curly braces, I can say, this pattern match is a little bit more tricky. Inside quotes, you can also do type variables. For example, I can say type, let's call this T1, which is actually genericize this. You know what? Let me do rocket science. Okay, so let me do type parameters. Let me do type parameters. Okay, and this is an expr list A. Fine. So I'm going to have a type T1. And if I have the expression, let's call this original, which is a list of this T1. And then we have .map with some sort of other variable like T2. And then you have a function, and then you have a map for another type T3 with like G. Then you will return the expression that combines the functions together. So, okay. So if I get a case like this, I'm going to return something, and in case I get something else, list, I'm going to return list. Okay. Does that make sense? Now, the implementation of this is a little bit tricky because you have to find out what the types are if you can compose the functions. I'm just going to keep things a little bit simpler. I'm going to return an expr of string just to have the functions printed out. So I'm going to say a mapped list with two functions. And I'm going to have f dot show and g dot show, just for you to see what kind of functions the compiler expects. Hopefully, I don't have case L find quoted required expr string. Okay, I don't have L. Maybe simple. I'm going to have curly braces. I like curly braces, actually. For those of you who hate curly braces and really insist on indentation, sorry, people. So let's call this description. Then I'm going to return an expr on that description. Okay, hopefully that's list A. No, I need string. Right, success, we want that. Okay, so let me have a list. List one as optimized list with list 1, 2, 3 dot map what underscore plus 1 map underscore times. Okay, look at this. We have map list with two functions. One is Scala int underscore plus 1, Scala int underscore times 10. Not only do you have access to the entire function, but if you really dive deep into the structure of that expression, you can pattern match those functions as well. So you can actually dive into the signature or into the implementation of the function, change that at will, compose the functions, or whatever else. I just wanted to have this demonstration simple so that you can see the functions, the implementation of function composition, and also do that recursively so that you can optimize an arbitrary chain of maps is a little bit more involved. I just wanted to show you the idea. Does this make sense? So, so T1 is a type variable. You can also have, so if you want to impose type restrictions, for example, type T1 is supposed to be an int, you'd have to do something like this. If you don't care about it, you can simply pass it as a type variable and the compiler will figure it out. So if I write something like this, it will still work. So you can say type T3 is a subtype of A, and then this T3 will have to reference to A within quotes is required given, yes. We need a little implicit here. So I talk at length about types and type ascriptions and this sort of thing in the course. I don't want to dive too deep into this because it's a rabbit hole, but for types that the compiler knows beforehand, so not necessarily custom types, the Scala compiler can synthesize type descriptions for the generic type parameter. If you have that sort of type description, you can infer or make the compiler infer type relationships between type variables and your own type. So hopefully that will do the trick. Okay. So in quotes, you can do pattern match on expressions. You can add types type restrictions, you can specify, for example, that the type T2 and type T3 are the same. So for example, I can say type T2 is a subtype of A, and you can say map T2 and map with exactly T2 later. So in this case, the compiler infers what type T2 is, and then for the later map, in this case, it will enforce that the type inferred must be equal to the type inferred beforehand. So there are a bunch of powers that you can use. I'm not going to, there are a lot of things that you can use in this case. Hopefully, by the end of this talk, at least you got curious about what kind of magic is possible with macros. I have one more demonstration to show you, and then I can close the talk and talk about macros and stuff. Another thing that is quite big in macros is the ability to dynamically inject ASTs manually at compile time. So in the case of the calculator language, you can transform the AST into another AST. For example, if you have numbers and you, for some reason, you're on planet Klingon and you want to multiply the numbers by 10, you can manipulate the AST and just multiply the numbers by 10, but you'd obtain the same kind of structure of an AST. In Scala or with macros, you can manually take a piece of the AST and replace it with something else. So I can simply take this div out and I can say number 45 or number 42. I can take that piece of AST and bring another piece of AST completely unrelated to what was originally in the code. So I'm going to show you that, and that feature is called reflection. When you speak about reflection, generally you refer to the JVM reflection at runtime. So for example, call a method dynamically by name. That is pretty tricky because you don't know if a method exists at runtime. If that method doesn't exist, your program will crash, and so on and so forth. We've all experienced this sort of problem with reflection in Java one way or another. In Scala, we have a sort of compile time reflection where you can dynamically insert ASTs into the code or into the expression that will be returned later. So manually build an AST based off of calling methods magically by name. Let me show you an example. So I'm going to have an inline function. Let's call this call me by name. By name is, let's call this dynamically. Dynamically with, I'm going to have a type which tries to find a method on this type. So I'm going to say an instance of type A and method name, so name as a string, and this returns maybe a string. So like always, I'm going to splice some quoted code. So call me dynamically impl on the quote instance and quote name. All right, let me define the method. So call me dynamically impl on the type parameter a for which there is a type in scope. So we talked about types. I don't have to talk about that anymore. Then we have the instance as an x per a. Then we have the name as an x per string. And finally, we're going to return an x per string. Okay, I'm going to leave this unimplemented for now because what I want to do with this inline method is to be able to say instance.method with some sort of argument. Let's call this like 42. Let's say that we want to figure out a method with the name name, whatever the method name is. So for example, if I have call me dynamically with some sort of class, so my instance, and the magic method, what I want to do is to invoke magic method on my instance on a parameter. For example, I can say my instance dot magic method on the number 42, assuming that this magic method takes an argument of type int and returns a string, let's say. So this is just an example of what you can do with just a few parameters and the ability to manipulate ASTs or the ability to build ASTs at compile time. So let me open up this, this thing. I'm going to pass my using quotes. Now, specifically for compile time reflection, this quotes thing will have to be named here because the Q thing will offer us some special APIs called reflect. So I'm going to have import QReflect star. And QReflect star gives me the ability to build ASTs, both in terms of expressions, convert them to values and vice versa, and also build ASTs that are, should I say, untyped, in the sense that they lose the type argument. And if we have a quote unquote typed expression or a typed AST, that's an X per A. We also have an untyped AST, which is subject to reflection, in the sense that you can search for fields, for methods, for type descriptions, for various forms of signatures. That is called a term. And term is far more general. It can express method calls, it can express mathematical expressions, it can express various pieces in the Scala language. And this term can be subject to various transformations. And this term gives us the ability to, for example, invoke a method. So I'm going to have a val my term as instance, which is the expression. I'm going to say instance dot as term. The as term method is given to me by the reflect package. So this is an extension method on expressions if I have the QReflect in scope. Now, this is kind of like a loosely typed AST. Untyped is kind of like an improper word. There's no such thing as an untyped thing in Scala. It's just like less beforehand known type information. So you can consider the terms as loosely typed. Then I'm going to have val, let's call this a method. And the API is, there's a vast API, by the way. So pretty much everything that you can express in Scala, like the ability to call a method, you can have nodes for that. So nodes in the AST. There is a method called select.unique. So this is what the compiler does to figure out which method to call. So when you say x.method on an argument, the compiler figures out which method to call out of those that are being defined. So we have select.unique, and select.unique will have the object on which we're calling the method. So I'm going to have pass my term, and then I'm going to have the name that the compiler will search for. So I'm going to have name dot value or abort. So I have to pass in a compile time known name, otherwise the code will not work. So this is find the method by its name. It's not unlike the kind of process that the compiler does if you have a class, let's call this magic class, and then I'm going to have a def magic method with an arg as an int, returns a string. I'm going to say, I don't know, this is Scala with the argument, and then arg. Clear. If I have val magic instance as new magic instance, magic class, if I say magic instance dot stupid method, which obviously doesn't exist, by the same process, the compiler tries to find. So it's a very similar process to what I'm doing here in the macro. The compiler tries to find a method called stupid method. Obviously, it doesn't find it, so it's going to obviously fail. Value stupid member. Stupid method is not a member. If it has a magic method on the value 42, this thing compiles and obviously runs the way that you like. So the select.unique is a process that the compiler does naturally, but the macro API offers us the ability to do that ourselves. So I'm going to say, find the method by its name, and then I'm going to have to build that AST node, which is called an application or an apply. So application or an invocation. And that is called apply. Apply with the method that the compiler supposedly found, method on the arguments. And the arguments are expressed as a list. And then I'm going to say, okay, you know what? I'm going to also pass my arg as an int. My arg as an int. Let me also quote it. Quote arg. Okay. And then I'm going to say list on my little argument. So this invocation is now the AST node that I will inject back. What I'm going to obtain is invocation. And then you have kind of like a Java style instance of thing, but since you're in the reflection package, you kind of have to know what you're doing. So you can say as x per of string in this case. hopefully that didn't some hard. Okay, arg dot string. All right, so the code compiled. Does this make sense? Find the instance, find the method, build an ASC node, which is the invocation of that method, and return that invocation as an expression of type string, so that the compiler then figures out in the code that the invocation of the macro returns a string, because we need type safety. So what I'm going to say, Val, let's call this dynamic invocation, is call me dynamically on my magic instance, the name magic method. So notice that I'm passing this as string and the argument 42. Now I'm going to save. And look at this. We have dynamic invocation, which is mi.magic method on the number 42. The compiler already knows that it's going to call that exact method because it found it. If this thing doesn't move you, spend like 5 seconds. Like, is this magical or not? I'm calling a method by its like string name. If this thing doesn't exist, like stupid method, obviously this doesn't compile. The stupid method is not a member. Is this cool or not? I personally think this is pretty goddamn magic. This is what I had prepared for this talk. Thank you for coming to the talk. I'm waiting for questions. I'm not sure I can answer all of them though.
Well, I haven't really dabbled around in Scala 3 a lot, and they've kind of translated implicit into something else. And I think you might have discussed it at the top. I'm still trying to compile this. But can you implicitly define an inline def so you don't have to explicitly call the macro and do like the magic, but without explicitly having to call the macro all the time?
I don't think I caught that. I don't think I understood the question.
So you know how you have your inline defs?
Yeah.
Can you kind of do that implicitly, basically? I know Scala 3 has removed implicit to that the way it is in Scala 2.
Yeah.
Can you do or replicate that kind of behavior in the inline def?
There is a limited ability to synthesize givens, like implicit values, via macros. So you can do type class derivation, for instance, based on reflective values, like names and fields and whatever. You can inspect the structure of the data. So for example, you can automatically derive JSON serialization for case classes, which is like a very basic, very popular use case for libraries. You can automatically synthesize givens in the sense of encoders and decoders for JSON based on the structure of the class.
Yeah.
You can you can definitely do that, and macros are very powerful combined with implicits.
Yeah, exactly, because I think that's what you kind of get into with the reflective stuff.
Yeah. This is just a demonstration of the kind of power that is possible. There's far more than I could demonstrate here.
Yeah, exactly. Yeah. Oh, yeah, it's very nice, very, very powerful.
Have one in the back.
To the previous question, there's also a discussion to propose like inline conversion type class, which will be, so there's conversion type class in Scala 3 that allows you to define an apply method, which will convert a type to another type. There's a proposal, I think, to discuss an inline conversion, where the apply method is inline, and therefore it can delegate to a macro, which means that the conversion logic from one type to another can become a macro, and it will be automatically instantiated by the compiler when you're receiving one type, expecting another, and there's a conversion in scope. So just a comment on that. But the question that I had is, what are your thoughts on the fact that the Scala 3 macros have been sort of nerfed in comparison to Scala 2 macros, like the macro notations and other things cannot introduce new type checked members? It's sort of very limited within the type checker. Do you think that's a limiting factor compared to Scala 2, where you could do anything? Or should we wait for like another mechanism, or what are your thoughts?
I just think that Scala 3 macros emphasized strictness and safety rather than the kind of cowboy macro dangling that we used to do in Scala 2. So that's my current thoughts on that. I think macro annotations should come out of experimental at some point because they're super useful and we can synthesize very powerful code with very little, with very few definitions. So they would be very, very powerful and very useful.
So having some experience in, I guess, some experience in AOP and Flink, stuff. First of all, do you think there is any kind of limitation in terms of what you can do with macros in Scala 3? And these things people used to do in Java, like cross-cutting concerns, like let's say security logging and service management and stuff like that. Is there any kind of limitation in what you could do in Scala 3 of these? And there is kind of half more question. If you think there could be any limitation when you run this kind of code in Spark.
Spark, okay. Okay, big questions. There are some limitations on what you can do, but it's in the interest of safety and in the interest of adhering to the AST structure that Scala supports. So you cannot really do everything that you want. I do think that Scala macros, as they are, extremely powerful. So you can automatically synthesize or automatically infer dependency injection. So from Zio is a nice example of that because when you have you used Zio? Okay, so you know that the provide method where you can pass in that's a really powerful feature and it's not. It utilizes just the basic features of macros. It doesn't even use the full capability of it. So I think that macros have a huge potential to do away with the dependency injection or with the boilerplates or with the kind of stuff that they used to take a lot of our brain power. So in that case, they're very powerful. In the sense of, in the Spark realm, we'll have to wait until Spark supports Scala 3, really. So, I mean, officially, because you can technically write Spark with Scala 3 if you do the cross compilation with Q13, but we'll have to see what Spark on Scala 3 supports.
Thanks for the talk. I was wondering, like, which libraries can you actually specify to be used in the macro implementation itself? Like, does it use the same libraries that your normal code uses?
You can inject. You can. I do an experiment in the course where I use a class loader at compile time and dynamically load a class while the code's compiling, which is something that you shouldn't really replicate. You shouldn't do at home, but it is possible to use external libraries, for example. Not in the same style that you can do in like regular import cats implicit star and do whatever you want, but you can use any JVM library for sure.
I have so many questions I'd love to ask, but I'll try to keep it to maybe just two.
All right.
Easy ones. So the first question is, where's the documentation for this other than your course? So like you showed some pattern matching syntax, which is new syntax. Where would I find out about that?
There is a reference. So there is the Scala 3. Yeah, it's the specification of how macros are laid out, and you can see the syntax there with like the grammar and stuff. It's a bit arcane and it's a bit technical, or I mean, technical. It's a loaded term. It's a bit involved or academic, let's say. Yeah. You can parse it, but yeah.
Takes a while. Gotcha. Okay, thanks. And question number two, another short one. So perhaps you could talk a bit about the limitations of macros, sort of building on what Anton mentioned, or sort of alternatively, when you specify these macros, they were constrained by input types and output types. So I know like a transparent macro can refine a type, but it doesn't
Yes.
seem like you can construct new types from within a macro. So,
You can do that.
okay.
You can synthesize new types at compile time. This is, let me show you.
My questions are short, but your answers don't have to be.
I called it black magic for obvious reasons. Oh, okay, I have it open. So
bigger.
yeah. In synthesize types at compile time, I have a little project in the course, which is called TypeSafe JDBC. So TypeSafe JDBC looks at the specification of tables in a database, in a running database at compile time. So at compile time, you can connect to a database, figure out the schema of the table, and from the schema of the table, you can look at its members and synthesize a new type with those fields statically typed in Scala. For example, so we spent like a couple hours building this in the course. And in the TypeSafe JDBC playground, I have, forget about these weird signatures here. Look at this. So demo JDBC reader says, JDBC communication run query select star from users. This is so this connects to a database. So I have a Postgres database just to demonstrate this. Connects to the database, figures out the schema of the table, takes all the fields and all the types of that schema, and synthesizes a refinement of a basic class, and then adds fields corresponding to the names of the columns and the types of the columns from the table at compile time. So then you can do rows for each print line, hobbies for, okay. So run query, demo refine types, okay. So I can forget about this. This is a false alarm. This is in metals. Okay, so I can say select star from users. I have this query result decoder.make, which is a big macro that does everything that I just described. Then I say run query at compile time, and then run query. The ability to run query is actually fetching users from the database, but the types are already known at compile time. So I can say type rows map underscore dot name. Name is a synthesized field in the class. So you can synthesize new types at compile time. I'm not sure how to answer the question, but it's, yeah.
Can I ask a question to follow up to that?
Yep.
So what you've shown here is really cool because what we're actually seeing is that we have a macro, but the stuff that's executing in that macro is not pure, right? So as opposed to a pure transformation of just an AST to another AST, we're actually performing a side effect. But given that this is going to be run at compile time and I might have an incremental compiler, I guess I wouldn't know when this side effect was going to get performed. So with that in mind, how should you handle side effects in macros?
I mean, use the force. If you're in the macro and you really know what you're doing, you're kind of on your own to a degree. I mean, the macro API helps a lot, and hopefully I could show you some examples, but you have to kind of know what you're doing. The Scala compiler cannot help that much in that sense. In this case, it's akin to regular Scala code, which the compiler cannot figure out if it's producing a side effect or not. So you kind of have to be careful. Trademark. Anyone?
If you're deriving a database or a table into a type of macros, and this is kind of getting off topic though, and you've got say a number and you've got strings instead of a number, how would you use macros even though you don't have the help of runtime to handle those kind of errors and those assumptions that you're whatever table or name is actually a number or a number is actually a name, and so on and so forth. Well, how would you accommodate to that?
So the idea behind this project is that if you change the schema of the table, if you alter table and you change the name from a string to an ID like a number, you compile again and this connects to the database and fetches and resynthesizes the type.
Oh no, I meant like if you had like rows that had a mix of numbers or strings that didn't conform to the type that you were expecting.
I didn't go that far, man.
Yeah.
I just showed you what's possible.
Yeah, no problem. That's why I say it was going.
Just an example that you can jump to hyperspace, but that doesn't prevent you from hitting an asteroid. You know what I mean?
Hello. So I was experimenting a bit with macros once, and I wasn't like able to find out how do you test the error cases because like my little example was like I have an enum and I want to discover the children, but then I don't want this to compile at Siltrate.
Yeah.
So I was writing a test and the test wasn't compiling.
Yeah.
So how do you test that? Does the course show or maybe I shouldn't pay for it? No.
I was talking to Nick. Yeah. I don't have a straight answer for that. I mean, when you're in macro land, you lose access to the regular things that we normal software engineers writing regular code have access to. We lose access to a debugger. We lose access to the kind of stuff that we normally use to make our code correct. When we're in the macro land, it either compiles or it doesn't. The most that you can do is rely on the error examples. But really, guys, this is asking for the world. Macros are really powerful as they are. Let's be thankful for that.
Can you use IntelliJ to write macros?
You can, to a degree. I mean, I'm using SBT as the source of truth. Notice that I'm not using either Bloop or anything else to. So SBT is personally for me, SBT is the source of truth for both IntelliJ and Metals, if I write.
Very much, everybody.
Thanks so much.
Okay. Please remember, our next meetup is on the 6th of March.